Hi there, welcome to another video from Hegarty Maths. It's Mr. Hegarty here, and in this video we're learning about differentiation from first principles. Now this is a really exciting topic in a new field of maths we probably haven't seen much of before, and in this lesson I want to introduce you to what differentiation is and why it works. Future lessons will show you how to apply the rules of differentiation, but this lesson we're trying to go for some understanding. So let's start with the basic idea. What on earth is differentiation all about? Well, differentiation is a method or mathematical technique for finding the gradient or rate of change of a function at any point algebraically. And differentiation is a technique within the area of maths called calculus. Calculus is all about studying things that continuously change. So our objective is for a function, let's say y is equal to f of x, at any point we want, like this point here, can we calculate the gradient algebraically? Now, some of you may say, Mr. Hegarty, why do we need differentiation? We know how to work out the gradient of various functions. So you're right to some extent. Let's talk about what you guys already know. Well, you guys know that for straight line graphs, the gradient or the rate of change is always constant, and of course you can work it out. You can use the formula the difference in y's divided by the difference in x's to work out the gradient. And so for straight line graphs we don't need the technique of differentiation. We've got a technique that's perfectly suitable. What about for curves though? Is it as easy to work out the gradient at a point on a curve? Well, we have touched upon these ideas. Let's just talk about where we've seen them. We have seen them in previous lessons on Hegarty Maths where we worked out the gradient of a chord, right? A chord, and we said that was the average gradient between 2 points on a curve. So that's not quite the gradient at a point on a curve, it's an average gradient between 2 points on a curve. So that wasn't quite what we were after. But we actually were able to work out the gradient at a point on a curve, because the gradient at a point on a curve is the same thing, is equal to the gradient of the tangent to the curve at that point. So what we did previously is we said, right, let's draw a tangent line, let's work out the gradient of the tangent line, which we can do by doing difference in y's divided by difference in x's, and that's going to give us the gradient at the point on the curve. And that was great. We were able to do that. However, there were some limitations with that method. For one, it's a bit annoying that you have to have the function in front of you on a graph paper and draw a tangent out and work out the gradient of the tangent. And secondly, it's a bit inaccurate, but especially when doing it by hand, because your tangent might be slightly off and you mightn't get the perfect 100% accuracy on the gradient therefore. So the difference with differentiation is it's going to be an algebraic technique. We won't have to see the function or the graph of the function. We can use some algebraic manipulation to find a way of getting the gradient at any point we want to, and we won't have to draw the gradient line each time. So that's going to be pretty efficient for us and pretty cool. So let's try and say how this technique works. Why on earth does it work? Where does it come from? In most courses, you probably won't need to know why, to be honest with you. However, at Hegarty Maths, we want to explain why things work. The future lessons will obviously apply differentiation and use the basic rules, but in this lesson, we want to take our time and make sure we know what on earth this technique's about and where does it come from. So let's start with our problem. We've got a curve, y is equal to f of x, a function, and we've plotted that on an xy axis. Now, our objective is to, at some point x on the curve, the point has coordinates x, f of x. At that point, can we work out the gradient at that point on the curve? Well, we know we can the old way. We draw a tangent to the curve. The gradient of the tangent is equal to the gradient at that point on the curve. So I've drawn in the tangent just to remind us of our old ways. But we're not going to do that in this particular lesson. We're going to think to ourselves, how can we find a technique without having to draw stuff out that's going to help us work out the gradient at that point? Well, this is what we do. we're very interested in this coordinate here and the gradient of at that point on the curve. But we say to ourselves, look, let's go a little bit more to the right of where we are at x. Let's go a little distance. Now, h looks big here, but just imagine we've only gone a little distance, h across, till we get to the x coordinate x at h. And we say, where is that on the curve? Well, it will be at the point x at h, f of x at h. So what we've done is we've gone a little bit more to the right on the curve. In short, we've gone h across and we've gone this distance up, which is f of x at h, take away f of x. Now, why are we doing that? Well, if we were to draw a chord between those 2 points, right, we can work out the gradient of that chord because we know this coordinate and this coordinate. So we can work out the gradient of that chord. You may think to yourself, so what? Big deal. We're trying to work out the gradient of the tangent to the curve. Well, you're right. Just bear with me for a second. To work out the gradient of the chord, we can do it by doing the difference in y's divided by the difference in x's, which is going to be, with this little animation, hopefully this is clear, the difference in y's is f of x at h take away f of x, and the difference in x's is going to be just h. So the gradient of that chord is given by the formula f of x at h take away f of x, all divided by h. Simply difference in y's divided by the difference in x's. Okay? So we can work out the gradient of this chord. And my assertion to you is I believe that the gradient of the chord is fairly close to the gradient of the tangent. Now, I know from this picture in particular, the gradient of the chord is bigger than the gradient of the tangent. The chord is a steeper line, it's going to have a bigger gradient. But it's an approximation. And in particular, things are going to get better as this h is smaller and smaller. So, let's just say for now that you agree with me that the gradient of the tangent to the curve can be approximated by the gradient of the chord. You may disagree right now and say, well, I'm not sure about that. Let me show you what happens when h gets smaller and smaller. As h gets smaller, can you see that chord getting more shallow? And more shallow again. The gradient's reducing. It's reducing more. This little distance h, I'm just thinking of it as a tiny distance across. I'm making it smaller and smaller and smaller. And hopefully you can see from where we started off, the gradient of that chord is getting much, much closer. The steepness of that chord is getting much, much closer to the steepness of that tangent. Until the point where that h is so small, watch this last step, is so small that the gradient of that green line you can hardly see is almost identical to the gradient of the tangent. In fact, if I made h smaller and smaller and smaller and smaller until it tended to zero, until it got to zero, the gradient of the chord would actually give me the answer to the gradient of the tangent, i.e. the gradient of the curve at the point x. So what we say is the gradient of the tangent is approximated by f of x at h take away f of x over h. But as h tends to 0, the gradient of the tangent is actually equal to, and this is shorthand for limit, the answer you get when h tends to 0 of f of x at h take away f of x all over h. That's what that means. Or we say the limit as h tends to 0 of f of x at h take away f of x all over h. And we call that f primed of x, or the gradient function, or the derivative, and we give it this name and it's calculated as follows. Now, right now you might think to yourself, I'm not sure how that applies. We're going to apply this and use this formula to work out various gradient functions or derivatives to check they work. But just for now on notation, let's just say that f primed of x, we call that the gradient function or derivative if we can work this thing out. And it's so useful because if we can work it out, what it will give us is for any x value we want, it will tell you the value of the gradient of the tangent at the point x, i.e. the gradient of the curve at x, which is fantastic. Unfortunately, it's got some slightly different notation associated with it. You may see it in this form called f primed of x, or in this form, if you're given the function in terms of y, like y equals x squared, sometimes the derivative of gradient function is called y primed, and often it's also called dy over dx, or dy by dx. Now, That's f primed of x, that's y primed, and that's either called the derivative of y with respect to x, or we just say dy by dx. Now, I know it's slightly annoying that there's different notation for this. Just to give you a tiny little bit of background, these first two here were used by Newton when he was using differentiation techniques, and this one here was used by another mathematician called Leibniz. So they both were doing differentiation at roughly around the same time, and they both had slightly different notation for it, and those have persisted to the modern day. So when you see the derivative, you may see it of these forms or this form. Often in textbooks, dy by dx is more common. So we're going to see a mix of these throughout our lessons, but just to be mindful, they basically mean the same thing. So it's all very well and good. We've got this idea. We've seen it applied to a general function. How on earth does it work in reality? So let's try and apply this formula, which is called differentiation from first principles, to various functions and see what answers we get for the derivative or gradient function. So let's start with this one here. Our first example. Our function f of x is equal to x, and we're asked to find f primed x, the gradient function or derivative, from first principles. That means applying this limit formula we've just been shown. So just before we launch into this, let's just stop and think what we already know. This is a function of the form f of x is equal to x, or y is equal to x. And hopefully you guys know what the gradient of that is. That's a straight line. It's of the form y equals mx plus c, where m is 1 and c is 0. So the gradient here of y is equal to x is 1. We already know the gradient function, and for a straight line the gradient is constant for any value of x. And y, just if we were to graph this, y is equal to x looks something like this. And that has a gradient of 1. Every time I go across 1 unit along the x-axis, I go 1 unit up along the y-axis. It's got a gradient of 1. So just for our background knowledge, we already know the gradient function here. It's a straight line. We don't need differentiation, but we're just going to differentiate from first principles anyway, just to check that this technique doesn't break the rules that we already know are in place. So it's consistent with what we already know. So let's give this a go anyway. What is first principles? It's f primed of x is equal to the limit as h tends to 0 of f of x at h, take away f of x, all divided by h. So let's try and work out what f of x is. What's f of x at h? Let's substitute in. Let's simplify this expression. Let h become 0. See what we get out the other side. So f of x is equal to, given in the question, x. F of x at h is going to be, substituting x at h in this function, simply x at h. So f primed of x is therefore the limit as h tends to 0 of x at h, take away x, all divided by h. And hopefully you can see there's an x here, subtracting another x here, so that simplifies. And we've got the limit as h tends to 0 of h over h. H divided by h is simply 1. So this is the limit as h tends to 0 of 1. Well, hold on a minute. 1 will always remain 1 no matter what h is. H can change to 0 all it wants. 1 still stays as 1. So the answer here for the derivative or gradient function or f primed of x is simply 1. i.e., when f of x was equal to x, f primed of x, the gradient function, was equal to 1. And we have done this technique from first principles. And notice we got a gradient of 1, which is what we already knew to be the case. So this new technique of differentiation, although not useful for straight lines, we don't need it, actually didn't break what we already know is true. So that's a good sign. Now let's apply the technique to curves. Here's a curve. See if you can find f primed of x, the gradient function, from first principles. So Always start with defining f primed of x, or the gradient function. It's the limit as h tends to 0 of f of x add h, take away f of x, all divided by h. What's f of x in this case? F of x is equal to x squared. What would f of x add h therefore be? Well, it's just substituting in would be x add h, all squared. Now, it's really handy when we're doing these questions to have a fully expanded out expression. So I don't like leaving it in that form. I'll expand it out and get myself x squared plus 2xh plus h squared. And I'm going to use that when I'm substituting in rather than the bracket version. So let's substitute in here. We've got the limit as h tends to 0 of f of x add h, which is this. It's x squared add 2xh add h squared. Take away f of x, which is x squared, and that whole result divided by h. Hopefully you can see here the first term and the last term eliminate each other, and what we get is therefore the limit as h tends to 0 of 2xh add h squared, all divided by h. I notice there's a common factor of h here, so I'm going to factor that out of the numerator, and that's going to be the limit as h tends to 0 of h, 2x add h, like that, all divided by h. And we've got a common factor of h multiplying on the top and bottom on the numerator and denominator. They cancel or simplify to 1, and this ends up being the limit as h tends to 0 of 2x add h. Now, we've done all our algebra manipulation. We're down to our simplest expression. What happens when h becomes 0? Well, this bit here just becomes 0. So we're left with 2x add 0, which is just 2x. So the answer here is 2x. So f primed x, the gradient function, or the derivative, is equal to 2x when the original function was equal to x squared. And we're done. We found the gradient function from first principles. Next question. Pause and have a go yourself. So here we're given that f of x is equal to x cubed. Find f primed x, the gradient function or derivative, from first principles. And we're also given a little fact here. It says you may use the following fact. We'll see if we need it later. So let's all start with what is f primed x. F primed x, the gradient function or derivative, is given by the formula the limit as h tends to 0 of f of x add h, take away f of x, all of that divided by h. So let's state what f of x is. We're given it in the question. It's x cubed. What's f of x add h? Well, just put in x add h there. It's going to be x add h cubed. Now remember I said earlier, we don't want bracketed version when we're doing this manipulation. We want the expanded version, and that's where the little fact given to us in the question is handy. We're told the expanded version of x add h all cubed, which is simply x cubed add 3x squared h, add 3x h squared, add h cubed, which is dead handy because we're going to be able to substitute that in. So let's substitute that in to our f primed x formula. F of x add h is going to be x cubed, add 3x squared h, add 3x h squared, add h cubed. Take away f of x, which is subtract x cubed, all of this divided by h. Now hopefully you notice the first term x cubed and the last term subtract x cubed eliminate each other, and we simply get the limit as h tends to 0 of 3x squared h plus 3x h squared plus h cubed, all divided by h. Hopefully you can spot there's a common factor of h floating around on the numerator, so let's factor that out. This is the limit as h tends to 0. Factor that h out and we get 3x squared plus 3xh plus h squared, all divided by h. And we've got a common factor of h on the numerator and denominator, which cancel or simplify to 1, and we get, therefore, this is the limit as h tends to 0 of 3x squared plus 3xh plus h squared. Now, at this point, we've simplified as much as we can. What happens when h becomes 0? Well, this disappears because it's going to be 0 times 3x. This disappears because it's going to be 0 squared, or 0 times 0, which is 0. And we're just left with 3x squared, which persists. So the answer here is 3x squared, f primed x, the gradient function, or the derivative, is 3x squared when the original function f of x was equal to x cubed. And last one, do pause and really try this one yourself to check you can do this technique. So again, from first principles, we want to work out the gradient function. That's defined as f primed of x, the gradient function or derivative, is the limit as h tends to 0 of f of x at h, take away f of x, all divided by h. And let's go over here and state what f of x is. F of x is equal to x to the power of 4. F of x at h, which we're going to have to substitute in, is therefore going to be x at h to the power of 4. But really helpfully, we've been given the expanded version of that, which is x to the power of 4, 4x cubed h, plus 6x squared h squared, plus 4xh cubed, plus h to the power of 4. So let's substitute into our formula the limit as h tends to 0 of f of x at h, which is x to the power of 4 plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the power of 4. Take away f of x, which is x to the power of 4, and all that expression divided by h. As we've seen previously, that first term and that last term end up eliminating each other, and we get the limit as h tends to 0 of 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the power of 4, all divided by h. Again, with these, we often spot a common factor, and there's a common factor of h floating around, which we can factor out of the numerator. So this is the limit as h tends to 0 of h, 4x cubed plus 6x squared h plus 4xh squared plus h to the power of 3, all divided by h. And we've got a common factor of h on numerator and denominator, and they cancel, or h divided by h simply gives us 1. And therefore we've got the limit as h tends to 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. Now, we've done all our algebra work. What on earth happens when h is actually 0 or tends to 0? This gets eliminated because 0 times 6x squared is just going to be 0. This gets eliminated because h squared, 0 squared is 0, and this will be eliminated as 0 cubed is 0. And we're simply left with the answer that f primed of x is equal to 4x cubed. So when f of x is equal to x to the power of 4, 4x cubed, f primed of x is equal to 4x cubed. So just before we go on and start using differentiation more widely, let's just recap what we've learned. We've learned that the gradient function is given by the formula the limit as h tends to 0 of f of x at h, take away f of x all over h. And that was essentially working out the gradient of a chord that's a tiny little distance h more across from our coordinate x. And that was the gradient function or derivative. And what we did is, in various cases, we worked out f primed x, the gradient function, with simple functions. So when f of x was equal to x, f primed of x was equal to 1. When f of x was equal to x squared, f primed of x, or the gradient function or derivative, was equal to 2x. When f of x was equal to x cubed, f primed of x, or the gradient function or the derivative, was equal to 3x squared. And finally, when f of x was equal to x to the power of 4, f primed of x, or the gradient function or derivative, was equal to 4x cubed. In future lessons, you may spot a pattern that's happening here. So have a ponder if you can spot what pattern is happening. We will come up with a pattern to make differentiation much quicker for us, and we won't have to do it from first principles each time. But this lesson was just to introduce you to why the idea works and where it comes from. And that's it for this lesson. Thanks for watching.